part, binary bits problem and Fibonacci numbers. Two problems we study in this module. A, B, C, D. Part A and B for the first problem, binary bits problem. Part C and D for the second problem, Fibonacci numbers. Let us start. B.1, reduce problem size by half. So that's the special property of this problem. Let us look at our problem number 10, count binary bits. Let us look at the question first. Given a positive decimal integer n. Here you can see we put this decimal, because usually we do not need to mention it, right? By default, we use decimal. But because in our goal, in our question, we want to look at the binary expression. So that's why we use decimal versus binary. The question, find the number of binary bits in its binary representation. Okay, it looks not very hard. This kind of calculation, not very hard, but there are several interesting techniques we can learn from this problem. First, let us review the binary expression a little bit. How do we use a general expression for the binary expression of a given positive integer? Here we can write general formula in this way. The base is 2. The base is 2, power of 2. Okay, power of 2. Corresponds to different positions. Then the bits numbers, B0, the coefficient B1, B2 through BS, subscript S. These coefficients, they are bits numbers. That means they only take a 0 or 1. All right. Then we also have the most significant bit, B sub S, that cannot be 0. Okay? In order to represent, in the good way, in a good way, so we require this obvious condition. Okay, all right. So then that means B sub S must be 1. Okay, all right. Then the answer with this expression, you can see the answer we want to find in the question must be S plus 1, because we have this many number of bits in the representation. All right. So you can see in order to find the answer, we just need to find S. What is the value of S in terms of n? Right? The formula should only contain n. In other words, we just need to find an expression containing the variable n that gives us the value of S. That's what we need to do here. All right. Now, so let us do some further analysis here. First, insight. The most important thing, insight in the solution of this problem. All right. Usually it is not easy to get the insight. Here, we want to use a special transformation to change the structure of this general expression. All right. How to get that? How to view that? How to get that? Because think about how do you manipulate this formula? How do you manipulate this formula? Right? You do not have many ways to do the manipulation. All right. Here, an obvious operation we can do on this expression, do division by 2, both sides. That is an obvious operation we can do, right? Division by 2. All right. After we do division by 2, all right, so division operation. Yeah, division by 2. The easiest division we can have on this expression. Yeah. Then you can see we take the floor function, the left-hand side, and over 2 floor function. All right, so the right-hand side, you can see B0 term is gone. B0 can only be 0 or 1. 0, it's nothing there. If it is 1 divided by 2, 1/2, floor function, 1/2 is gone, right? 1/2 is gone. All the other terms, you can do division by 2 with an integer value. All right, so you can see we get the new expression. So this expression can tell us a lot of things. Now, what can we get from this expression? What properties can we get from this new expression? All right, let us do some observation. First property, the least significant bit is removed. B0, that is the least significant bit. Yeah. We don't have it in the new expression. It is gone. Yeah, first property. Second, the number of bits is reduced by 1. Yeah. Now you look at the number of bits we need for this integer n over 2 floor function reduced by 1, comparing with the original binary expression for n, the number of bits 1 smaller. All right, that's the second property. The third one, the problem size is reduced by half. Yeah, the problem size approximately 1/2, not exactly, but very close to 1/2. All right, with these properties, next we want to get a recurrence relation for the solution function. All right, here let us get a recurrence relation from these 2 formulas. It's pretty straightforward. Yeah. First, we have this bin rec, yeah, the function name recurrence, binary recurrence. Okay, bin rec, yeah, of n. Yeah, that we define this function, the number of binary bits for integer n, positive integer n. All right, then based on the observation we have, you can see in order to get the left-hand side expression, let us represent the number of bits for the problem size n over 2 floor function. All right, we get that. After we get that number, add 1 back, because in our property we know this number, if we add 1 more to it, we get the original answer, the answer of the original problem. Yeah, so that's simple. So that is for the recurrence relation. Then we also need a base equation, base condition. Yeah, that is bin rec of 1. Yeah, when n equals 1, you only need 1 bit in your binary expression, so the answer is 1. Now, all right, then we can work on its solution. Okay, all right. First, before we try to solve this recurrence relation, let us write a simple program. Because with this recurrence relation, we can already write a function to find the answer. Here, this is the simple implementation of the recurrence relation. Okay, yeah, so you can see pretty straightforward. Yeah, I do not need to explain it. Yeah, you can understand easily. Yeah, but next we want to do the math operation. We want to use math to solve the given recurrence relation. So that will be much harder. Much harder, that means we need to pay a lot of effort in order to get a formula for this function. The formula, we want to get some nice formula for it. Yeah. All right, yeah. So let us work on it. All right, yeah. Here, we know to evaluate this binary relation in the program, n over 2 is just the shift function, right? Yeah, shift operation. Shift, the digit, decimal, point, and shift. Yeah, left, right. Yeah, in the binary expression, shift to the left, to the right. All right. Yeah, to the left. Yeah. All right. Left shift operation. Yeah. So that's pretty easy in CPU operations. That's pretty easy. Yeah. All right. But our basic operation we want to look at, that is the addition operation. Yeah. We want to see how many additions do we need when we do the recursion. Yeah. That's our new goal. Yeah, we change our goal a little bit. Yeah. All right. But if we change that goal a little bit, yeah, we use a new function a of n to represent the number of additions. Yeah. All right. So our recurrence relation should be like this. Yeah. So you can see after that, the recurrence relation and the original version, the same, right? The same, although their meaning different, but the same. Okay, yeah, yeah. It's okay. After we get the answer can be used for both functions, right? Both functions, bin rec function and a function, both functions. Yeah. All right. Yeah. Next, let us move to the solution part. Yeah. For the solution, first question, how to handle the floor function? Yeah. Because in the recurrence relation, the hardest part is the floor function part. We know it is not very convenient to work on an expression with floor function. Not very convenient. Yeah. If we can find a good way to handle the floor function, then we should be in a good position. Yeah. All right. First, let's look at the real meaning of the floor function. So that's the meaning of it. Okay, when n is an even number, n over 2 floor function equals just n over 2. Yeah. When n is odd, that function value equals n minus 1 parentheses divided by 2. Yes. All right. All right, so next, with this meaning, we want to work on the original, or we work on our target recurrence relation. Yeah. Let's look at the strategy. Yeah. This strategy we used several times before. Yeah. Here, we use it. because it is very effective. Yeah. Start with a simpler case. Yeah. That is the strategy we want. Start with a simpler case. Yeah. Here we have two cases, right? Even case for given integer n and odd case for given integer n. Which one you feel simpler, right? One is a little harder than the other one. Yeah. Which one you prefer to work on, right? Which one? Yeah. Yeah. In my view, yeah, I feel when n is even, it will be easier, right? So here, what do we wish to have, right? We wish to have an easier case, right? You do not wish to have a harder one, right? Yeah, usually people like to do something easier. Yeah. So that's the general way that people like to do. Yeah. All right, so here, let us look at in this case, when n is even, then n over 2, that no fractional part, so the floor function, when we apply it, nothing happens, right? Yep, so that's pretty convenient. Yeah. All right, but after that, when we do iteration, we apply that divided by 2 floor function another time. So this time, if n is just an even function, it may not be enough, because n over 4 floor function may cause some problem. All right, so in that case, we may like to have n over 2 is also an even number, another even number, right? So if n over 2 is another even number, then we don't have the fractional part, right? So you can see if we do this kind of assumption again and again, eventually we must have that n is power of 2. Now, only when n is power of 2, we have that. Now, when we do recursion, round by round, we have the integer numbers for n over 2 operation. Yeah, that's the most convenient case. Yeah, so that's the case we want to work on it. The simplest case. Yeah. All right, so let's work on that simplest case. Yeah. So we assume n equals 2 to the kth power. 2 to the kth. Yeah. Then k equals log base 2 of n. Yeah. All right. Yeah. Then, so let's continue to look at our new recurrence relation. This time in terms of k. Yeah. All right. Then we should have this recurrence relation. All right. Power of 2. Yeah. Inside the parenthesis, power of 2. Yeah. Let's do the work. Yeah. Let us apply this recurrence relation many times, as many as we need. So we should have this. The first time we get this. Second time, the power of 2 inside the parenthesis divided by 2. So we have the second equation. The third one, and so on. All right? Until we reach the bottom. The very bottom. All right. After that, we like to get the expression for a of 2 to the kth power. Right. In order to get that, if you have some experience, we should add up all the equations here, both sides. When you do that, you can do a lot of cancellation. Yeah, here, the left term, right term, red cross, we can cancel out. Another round cancellation, we cancel out in this diagonal way, all right? This kind of diagonal way, and so on. The last cancellation like that. All right. After the cancellation, then the remaining numbers we can have these numbers. What is that number? Can you see that expression quickly? What is that number? A of 2 to the k equals k plus 1. Why k plus 1, right? Why k plus 1? First, this number, based on the base condition, it equals 1, right? That's 1. Then, how many equations do we have? How many rows do we have, right? Count by reference. Do you still remember that technique? Count by reference. Here we want to count number of rows. Can you find appropriate reference that can be used for the counting? Now, here, look at the superscript. Exponent number, superscript, right? So each row corresponds to one superscript. The bottom row corresponds to superscript 1, 2, 3. Every time we increase the number by 1 until we get a k. What is that number? Total number of rows, k. Because our references, we use integer numbers from 1 through k, consecutive integer numbers from 1 through k. So k rows, k rows plus that base number 1, so k plus 1, right? So we get this expression. At the end, we need to go back to the n-based representation, n-based, the original variable n. So now we should have this. A of n equals 1 plus k. K, we use the log base 2 of n. Now you can see we get a pretty neat expression, right? How neat it is. Pretty neat, all right? But there is one condition here. N must be power of 2. Only when n takes a power of 2, you have this expression. If n does not take power of 2, we don't know what is the new expression. We don't know. But if you don't know, can you guess it? Can you make a guess? Can you make a guess? Many times we need to make a guess in problem solving. Here, we need to make a guess here. All right? For the general case, that means n is not necessary power of 2. Can you guess a of n equals some reasonable expression? Because when n is not power of 2, this term may not be integer. Most likely, it's not an integer. But the a function must be an integer, right? How do you make a non-integer expression to be an integer expression? We need to make, fill that gap. There is a gap. We need to fill that. That is a reasonable guess. A of n equals floor function of log base 2 of n. Floor function make that log expression integer. Floor function. Okay? But some of you may ask, why we do not use ceiling function here? Ceiling function can also give us integer expression. Yes, it's correct. Why we take the floor function, not the ceiling function? The answer is easy. We can check it. We can check it using some simple n number to check which version is correct. The ceiling function version or floor function version, which one is better? Right? So let us look at n equals 3 case. When n equals 3, all right, integer 3, if you want to represent as binary number, binary expression, it is 1, 1, right? How many bits do you use? 2. So the answer is 2, right? All right. Let us use the formula here. 1 plus log base 2 of 3, we know log base 2 of 3, 1 point something, right? Larger than 1, but smaller than 2. Yeah, because 3 greater than 2, less than 4, right? 2 corresponds to 1 after you take log base 2. 4 corresponds to 2 after you take log base 2. Yeah, so 3, it should be 1 point something. Okay, 1 point something. Yeah. Then 1 point something, if you take the floor function, you get 1. 1 plus 1, 2, right? If you take the ceiling function, you will get 2. 1 plus 2, 3. But our answer is 2. That means the floor version is correct. If we use a special number n equals 3, we can eliminate the ceiling function version. So we should bet on the floor function version. All right, so that's our 8.1 video. In the next video, I will prove that the floor function version formula is correct. All right, so let us start.